Welcome to the next installment of Mr. Horta's videos on particle physics for the AQA A-level syllabus. Today I'm trying something new. Rather than doing a PowerPoint, I'm recording something whereby I can use screen share and some handwritten notes because the diagrams I want to draw and some of the things I want to write out are quite time consuming. So I hope this is helpful. Two things we should take into this video and thinking about annihilation and pair production. One is a new unit of energy that I've only introduced recently, the electron volt. And as I pointed out in class, we use this unit because it's a useful unit in the area of particle physics, just like we wouldn't use centimeters to measure the distance between Nottingham and Manchester. We don't use joules generally because they're just too small. So we always have to convert to joules when we're using any formulae, because formulae always take the SI unit. But when we're working, quite often the examiners will ask us to work in electron volts or give us data in electron volts, because particle physicists generally in their day-to-day work use electron volts. The other thing is the Planck formula here. So the Planck formula is true for all electromagnetic waves, and it tells us the energy of the individual photons. So remember, sometimes we treat electromagnetic waves as waves with a frequency, a wavelength, and a speed, c being the speed of the light. But sometimes we treat them as individual discrete particles called photons. And the energy of those photons goes up as the frequency goes up. Or equivalently, we could say the energy of the photons goes up as the wavelength goes down. And that's what the Planck formula allows us to convert between. We'll also be using quite heavily the page 2 of the formula sheet, which gives us some information on the rest energies of the particles that we're interested in. And in particular, we'll be interested in the electron, positron, and also the proton and neutron, but the examiners could ask about any of them. So mass by E equals mc squared is effectively a form of stored energy. And rather than us use E equals mc squared, the examiners give us in mega electron volts the amount of energy stored in the mass of an electron. So if I can destroy that mass, if I can turn it back into energy, I get 0.51 mega electron volts of energy from the electron's mass. And you'll see a little bit how that works as we move onwards. I know we started this in class, but I just got pipped to finishing by the bell. So we're going to start the example from scratch. Okay. So the general diagram for annihilation is that a particle and its antiparticle come together, and in the event that occurs, all of the mass of those two particles is converted to energy. That's added to any kinetic energy that the particles had, and all of that energy is divided equally between two photons. So the diagram is often shown like this. So we've got two particles coming in, always a real and an anti-version of the same particle. And we've got two photons coming out. Now those two photons, for the purposes of A-level, are identical. And to find out how much energy they've got, we find out what's the rest energy of our two particles, and then we add any other types of energy. And for the purposes of A-level, that will be any kinetic energy. So if we start with the most basic, we assume the kinetic energy is negligible. So we say something like a slow electron collides with a stationary positron. Now, the examiners, by saying slow, are telling you that the kinetic energy is so small compared to the rest energy that we can ignore it. So all we do is a conservation of energy situation. So the total energy in is equal to the rest energy, which equals 2 lots of 0.511 times 10 to the 6 electron volts. Now, that energy is split. Oh, well, let's give a total. So that's 1.022 times 10 to the 6 eV. Now, that energy is split between 2 photons. So we need to show this to the examiner. There's no good missing this step out. They won't award you all the marks. Right? They want to see that you understand there is a total amount, because sometimes we're going to have to add some kinetic, and then we divide the total by 2. So the energy per photon, and we often use that gamma symbol for any type of photon, is equal to 1.022 times 10 to the 6 eV over 2. And we're back to the 0.511. Now, I know I've rounded this from the formula sheet, and clearly in the exam you would need to use the full data. So the question might then come, what's the frequency, or what's the wavelength of those photons? So the first thing we have to do, so there would be a mark at this stage for calculating that, but we'd have to go through this process to get the mark. If we just gave that answer, we wouldn't get it. And then we'd have to say the energy in joules is equal to 0.511 times 10 to the 6 times 1.6 times 10 to the minus 19. And we'd have to get some answer for that. And then if we want the frequency, well, frequency equals energy divided by Planck's constant. So we'd put that number in, and then we'd put divided by Planck's constant. I'm going to show you that on the calculator, because I'm concerned that some people are still not using the 10 to the x button. So what should this look like? It should look like 0.511 times 10 to the 6 times 1.6 times 10 to the minus 19. Note, if you use this button here, then the minus down here doesn't really work very well, and you've got to use this one. But if you use the times 10 to the x button that's next to the answer and the decimal point, then you can use the regular negative. So that tells us how many joules we've got. 8.176 times 10 to the minus 14. And now I need to divide by 6.63 times 10 to the minus 34. That's a very small number, so it's going to give me a big number because I'm dividing by it. And sure enough, 1.2 times 10 to the 20. Okay, now I forgot to give that intermediate number, but I should have given that. Okay, but I could do this. I remember it was times 10 to the minus 14. And if I do that, that shows the examiner I knew what the intermediate was, but better to write it down. 1.2 times 10 to the 20 hertz. Okay, and that's a high energy photon. Right, so when electrons and positrons annihilate, we get a pretty high energy photon there. We can move on from this to look at another annihilation situation. Here we've got a proton with some viable amount of kinetic energy, some significant amount, colliding with what appears to be a stationary antiproton, and we're going to get 2 gamma photons come out. So we want to look at the total energy input, and that now consists of 2 parts. So we've got the rest energy, which is equal to 2 times by, and then we go to our formula sheet, and we say, oh, well, here's the proton, 938.257 MeV. So it's 2 lots of 938.257, and the kinetic energy, which equals 100 MeV. So we could do that in our head, but we're probably at risk of making a mistake. So 2 times 938.257 plus 100. So that's 1976.514 MeV. So that's our total amount of energy, and that's going to be divided amongst 2 photons. So we might show the examiner the energy per photon is equal to 1976. Now I could do that, that would be fine to show the examiner I understand I'm bringing it all, but I can't be bothered to write it down. Divided by 2, and note how I'm trying to continually work vertically. If I don't do that, I can very easily end up making a mistake. So that's 988.257 times 10 to the 6 EV. So I double underline that because I'm showing the examiner I understand that's an end point for part of the question. That's how much energy each photon has. Right? But now they're going to follow on with asking me something like, what's lambda? Okay, well, lambda is hc over E. If you need to satisfy yourself of that, just pause the video here and rearrange that equation I showed you right at the start. E equals hc over lambda. It's vital that you can rearrange these things. Okay, but E has to, we can't do it in electron volts. It's got to go in SI units. Right, hopefully you're getting sick of hearing me talk about these SI units. So that's 6.63 times 10 to the minus 34. I think it's 6.63, but I might just check in a minute on the formula sheet. Times 3 times 10 to the 8, all divided by 988.257 times 10 to the 6. You're all thinking, oh, Holt has made an error here. But we can do it here, can't we, if we want to? We can show it as times 1.6 times 10 to the minus 19. We just got to be careful with the calculator. Okay, so it is possible. Now, you guys, I bet, all use the fraction button, this button here to do that. I'm so old that they didn't exist when I had a calculator at university. So I still type it in differently to that. But let's just check all my numbers while we're here. So formula sheet, scroll up, H, where is he? The Planck constant, 6.63 times 10 to the minus 34. Look, they even give you the units. That's really helpful sometimes to, like you see exam questions on the units of G, and it's there, and people forget and they have to work them out all for themselves. Okay, right. So let's have a look at this calculation then. So 6.63 times 10 to the minus 34 times by 3 times 10 to the 8. And I press equals at that point, right? And then I'm going to do divided by. Now I want to do a multiplication, so I'm definitely going to put this in brackets. 988.257 times 10 to the 6 times by 1.6 times 10 to the minus 19, and I get an answer, and that's a pretty tiny wavelength, and I'm thinking, gosh, am I sure that that's right? So it's sometimes really helpful to have an idea what we're expecting at these points, and you can only really do that by doing questions. The last thing I'm going to tell you to do in A-level physics is go and learn a load of wavelengths by heart. A few that you might get used to and so feel more confident is that the wavelength of light, I would say red light, is really quite common and probably worth learning by heart. So that's 600 nanometers roughly. So this is very high energy. if we're getting to a much shorter wavelength. Remember, the higher the energy, the shorter the wavelength. In fact, that's in the region of femtometers. I hope you were all screaming that at the screen while I was trying to grasp for the word. So that's of the order of a proton size, isn't it? Yeah, we've done the strong force. So that might be a good answer, and I will go and check after I finish the video that I've got it right. But that's annihilation. Now, because I've never used this functionality before, I'm not sure how well it's going to render an MP4 and how big that file is going to be. So I'm going to stop the video here and break it into 2 parts, just in case it all goes wrong.